Hey, welcome back to the lecture. In this lecture, let me demonstrate the operational modes of the Cortex-MX processor by using an exercise. Let's get into the IDE and let's create a new project. Let me create a new project. You can use the same workspace. Select the board. Let me give the project name operation modes. Select empty. Finish. Let's get into the source file main.c. Let me explain the operational modes of the processor using this code snippet. First, let's understand what's happening here. First of all, this file has three functions, and here is a main function. This is the first function which gets called after you reset the processor, which is actually not true because after reset, the reset handler executes first and reset handler calls main. But since we have not yet explored the reset handler and other things which you are going to explore later in this course, let's just assume that the main is the first function which gets executed right after the reset. Remember that after reset, processor always starts in thread mode. That means all these instructions will get executed in thread mode of the processor. Here I'm just printing some statements using printf library call, and after that I'm calling this function generate interrupt. This function is implemented right here. This function also will get executed in thread mode of the processor. That means all these instructions are executed in thread mode of the processor. Here what I'm doing is I'm just triggering some software interrupt by accessing the system level registers of the ARM Cortex-MX processor, which are mapped at these addresses. So don't worry about these codes because we have to explore a lot of other things to understand these codes. In this course, I have a dedicated sections to explain the system exceptions, interrupts, software interrupts, and various other things. You will come to know when you get there. All I'm doing here is generate an interrupt from software. At this line, I'm triggering the interrupt. When this line gets executed, interrupt will be triggered in the processor and interrupt handler will get executed. That interrupt handler is implemented right here. This is the interrupt handler or interrupt service routine, and this executes in handler mode of the processor. These two functions will get executed in thread mode, and this function will get executed in handler mode of the processor. Then what's the specialty of handler mode code? In handler mode, you have full control over the processor. You can touch any resources you want. You can access all the system level registers of the ARM Cortex-MX processor. You can change the interrupt configuration. You can modify some of the control registers. You have full access to the processor. That's the specialty of handler mode code, because handler mode code always executes in privileged access level. That doesn't mean that thread mode codes will not have privileged access level. Of course they have. By default, all thread mode codes have privileged access level. That's the reason why I'm able to change the system specific register of the processor in this code snippet. But I can restrict thread mode code not to touch or change any system level settings of the processor by changing the access level to the unprivileged access level. But no one can put restriction on the handler mode code. The handler mode code cannot be in unprivileged access level. It will always execute in privileged access level in ARM Cortex-MX processor. Let's copy this code, go to our project, and let's paste here. Let's execute this code on the target and let's analyze. Since I'm using printf, I'm going to use ITM based printing. Let me compile this project and let me just debug this. Here I'm going to enable the SWV, apply, OK. I'm about to execute the main function. This executes in the thread mode. But how do you know it executes in the thread mode? There are some status registers which can highlight whether the processor is in thread mode or in the handler mode. Let's go to the processor's generic user guide and just search for interrupt status or interrupt program status register right here. So about status registers, general purpose registers and special registers I'm going to discuss in the later lectures. There is a register called interrupt program status register, and this register has a field called ISR underscore number. This field, if it is 0, that means the code is executing in thread mode. Otherwise, if it is non-zero, then that means it's a handler mode. And these numbers represent the type of exception or interrupt it is currently handling. Because we enter into the handler mode only when there is a system exception or when there is an interrupt. That means whenever the processor is moved to the handler mode, this field will reveal you which exception or which interrupt caused processor to move to the handler mode. Let's observe this field using our debugger. Here, go to Window and go to Show View and go to Registers. That appears at the right hand side. Here, just expand this general registers and here it is. Go to XPSR. This is a program status register. Here you have to observe the first 9 bits, that is 0 to 8. And you can see that this is the first 9 bits and it is 0. That's why you can say that the processor currently is in thread mode. Let's do step over and let me execute generate interrupt function, and the control will come to the ISR when we execute this, because the interrupt is going to be triggered at this line in the generate interrupt function. So I'm going to keep a breakpoint here and I'm going to hit resume. Here it is. The control came to the ISR and here it is. This field got changed. This is non-zero. That means processor is in handler mode. And so what is this number? This number is 19. 16 plus 3, 19. You can compare that value with this field and you can understand which system exception or which interrupt triggered the handler mode execution. 16 means IRQ0, 17 means IRQ1, 19 means IRQ3. IRQ3 triggered the interrupt and that's the reason why processor moved to the handler mode. In the code, that is true. We are triggering the software interrupt for the IRQ3. Don't worry if you are not understanding what is this IRQ and what is IRQ3, why IRQ3 is RTC. All these things you are going to learn little later. The goal of this exercise is to demonstrate a switching between thread mode and the handler mode of the processor. Now let's do step over here and you can see that the processor returns to the thread mode here. It completes the ISR execution. The execution of thread mode code is resumed, isn't it? And you can see that the field is now cleared. That's about handler mode code execution and thread mode code execution of the processor. So the key takeaways from this lecture is there is only one way to move the processor from thread mode to the handler mode, that is by triggering the system exception or by triggering the interrupt. The interrupt may come from externally or you can use your code to trigger a software interrupt. That's the only way you can push the processor to the handler mode. When the processor goes to the handler mode, it executes the interrupt service routine or exception service routine related to the exception or interrupt which caused the processor to move into the handler mode. And in the handler mode code execution, the access level is always privileged. You can access any resources you want of the processor. That's it for this lecture, and in the next lecture let's understand about the access level, so how we can switch the access level between privileged to non-privileged or non-privileged to privileged. I'll see you in the next lecture.